Hello, my math people. Hopefully, you guys are all doing well and you're excited to learn some math. Today, we are going to learn about something called scaling. You might have heard of this before. Scaling is basically making something bigger or smaller. So, it's making things bigger or smaller. And we do this all the time, right? So if you think about scaling, somewhere we see scaling is like a globe, right? If you see a globe in a classroom, the world, that's not obviously the actual size of the world. It's been scaled down so that we could actually have a little model that we could play with. We see scaling with cars all the time. People will take vehicles, scale them down to be little toys, or even scale them just to try to design them because it's easier to work with a small model car when you're designing it than a really big model car. We also see scaling with maps. That's probably one of the biggest things we see is if you look on your map, the distance on your phone that it shows that you are away from Red Deer. Obviously, you're not one finger length away from Red Deer. You're actually a lot of kilometers away, but that map has been scaled. So it's been made smaller so you could actually work with it. Sometimes we scale up, so we make things bigger. That's probably more rare, in all honesty. But we do scale up. Think of your science class right now, which you guys are all in science. You guys look at things like DNA. DNA is obviously so small we can't really see it, but then we scale it up so that we see a big model we could actually look at and investigate and deal with. So it would be a use of scaling something up. I want you to take a second and think if you can find another way in which we use scaling. So what is another example of scaling? You can come up with anything. Just try to think of something that we make bigger or we make smaller for whatever purpose. Fantastic. Hopefully you came up with something. When scaling objects, we have to have a way to actually do it properly. So for instance, if I wanted to scale an entire car, I have to scale the tires at the same rate in which I scale the door, in which rate I scale the windows, in which rate I scale the hood of the car. Otherwise, I'd have a very funny disrepresented looking car. The way that we represent scales is by using ratios. So ratios is it's just a way to compare numbers. A ratio always looks like this. It's a number and then a colon and then another number. Such as this example down here, right? That would be a ratio of 1 to 30. When we scale something and we put a number and then to another number, the first number is the representation size. Sorry, I'm stuttering over here. This first number is the representation size. So it's what I'm turning something into. The second number is the actual size of something. So for instance, if I had this ratio of 1 to 30, 30 is my actual size. 1 is my new size. So if forever 30 long something is, I would now only be 1 long. This would be scaling down, right? My new size is smaller than my actual size. Let's see how this works. So if we had a scale of 1 to 15, what does that mean to have a scale of 1 to 15? And is this object getting bigger or is it getting smaller? When looking at a scale, the first number is my new representation. The second number is my actual length of something. That means for every 15, and we don't know the measurements, so that could be 15 centimeters, could be 15 meters, could be 15 kilometers, but for every 15, we now have 1. This is getting smaller. Wonderful. I want you to pause right now and read the next question. So what does the scale 3 to 2 mean? Is the scaled object bigger or smaller? I want you to try to answer both those questions. So pause the video, fill it out, then unpause and see if you got it right. Beautiful. So if I wanted to set this up, I would say that 3 is my new length, 2 is my actual. So for every 2, we now have 3. That means that I am getting bigger. If something used to be 2 inches, now it's 3 inches. If it used to be 2 kilometers, now it's 3 kilometers, right? It's getting bigger. Awesome. That's scaling and ratios. Now we're going to actually try to apply scaling and ratios. So we have the picture of a lion is being drawn using a scale of 1 to 50. What does the scale 1 to 50 mean? What does the scale, just a second. What does a scale of 1 to 50 mean? It means that for every 50, and they didn't give us units, they should have. We'll say 50 centimeters. For every 50 centimeters, the lion measures. We draw 1 centimeter. All right, this thing is definitely getting smaller. Right? If I'm looking at that, the new length would be 1 centimeter. The actual length would be 50 centimeters. What is the actual size of the lion? Something's missing here. Give me a second. Hi, sorry, I noticed something was wrong because that question makes no sense. What is the actual size of a lion? We don't know because there's no lion there. There's supposed to be a picture with this. I'll fix the notes. So on your notes, you should have a nice little picture of a lion. The lion is drawn over here. Watch this picture of a lion that I'm going to have. It's like, kind of looks like a flower right now, but that's just his head. And then he should have a body. And he looks so fierce. And he's got a tail. And then it tells us, oh, I'm so sorry. This lion in the picture is 2.5 centimeters. You should have that picture on the side of your thing. I don't have it, so I'm just drawing that beautiful picture right there. Now I can answer my question. It says, so what is the size of the lion? To figure the actual size of this lion, there's a systematic way and then there's kind of logical way. So maybe you can logically understand how these scales work. Maybe you're really good with scales and you can just answer and be like, oh, that actual lion is this long. Or maybe you need to have more of a process. I'm going to show you more of the process here. So for me, what I like to do is I like to take this ratio and I turn it into a fraction. And I compare it then to what my drawing is. Now, this fraction can go either way. You could either set it up as 1 over 50 or as 50 over 1. It can go either way. Whatever you're looking for, so if you're looking for the representation, then you would pick this one. Looking for new length. If I wanted to look for the old length or the actual length, I would pick this one. In our case, we're trying to look for the actual size of the lion. So what I want to do is I want to make a ratio of 50 over 1. That is my actual divided by my new. And then what I can do is I can take that ratio and make it equal to my actual length, which I don't know, divided by my new length, which was 2.5 centimeters. So what I've done is I've taken my ratio, I've turned it into a fraction where my actual is divided by my new. So it's 50 divided by 1. And then I said that must equal my ratio of whatever the actual line was, which we don't know, divided by my drawing of the line, which was 2.5. The reason why we do this is because now what we have is cross multiplication, where I can take this 2.5 and I can cross multiply it to the 50. This now gives me 50 times 2.5 divided by 1 will equal my actual length, which we don't know. If you put that in your calculator, 50 times 2.5, you end up getting that the actual length is 125. Okay, that can be really confusing, especially the first time we go through it. All right, so we're going to do a couple more examples of just the same type of stuff, and I'm sure that the calculations will get easier and easier. So if we look at this right here, we have, according to Google Maps, the driving distance from Sylvan to Red Deer is 23.9 kilometers. If the scale for the map above is 1 centimeter to 2 kilometers, how long is the driving distance on the map? Okay. We know the actual distance equals 23.9. We want to know the new distance on that map. So if I was actually to measure on that map how long that is in centimeters. The way in which we're going to calculate this new length is by taking this beautiful ratio up here and writing the new divided by the actual. So for us, in our ratio, this is the new, this is the actual distance. So I'm now going to set up my formulas using that. So I'm going to have 1 centimeter divided by 2 kilometers equals my new distance, which I don't know, divided by my actual distance, which is 23.9. And it's 23.9 kilometers. Okay, so do you see how I've set that up? I'm going to try to slide this over because I'm running out of space here. That'll have to do. So what I did was I looked at the question. I figured out what it wanted. It wanted me to figure out what's new. Because it wanted me to figure out what's new, I used this formula right here, which is new divided by actual. I then took my ratio and I wrote it as the new length divided by the actual length, which is right here. And that equals my new, which I don't know, divided by my actual, which is 23.9. What this allows me to do is now do ratio math, where I can cross multiply this 23.9 kilometers. So that I now have, I did not give myself enough space to work on this document. I'm very sorry for that. Give me a second. Maybe this will help. Perfect. So when I cross multiply, I now have 1 times 23.9, and then I divide it by 2. You don't have to worry about kilometers, centimeters, that kind of stuff. I'm just looking for numbers. We can add in our units later. But if we do that calculation, that should tell me my new distance on the map, which is the drawing that we see up there. If you calculate that, 23.9 divided by 2, you end up getting 11.95 is my answer. And because it's the drawing, that would be 11.95 centimeters is what's on that drawing. Part B. On another map that uses a scale of 1 centimeter to 5 kilometers, Mr. Kennedy measures the distance from Sylvan Lake to Airdrie to be 126 kilometers. How far apart are Sylvan and Airdrie on the map? So what I'm looking for here, how far apart are Sylvan and Lake on the map? We're looking for the new measurement. That means I want to use the formula new on top, actual on bottom. Whatever you're looking for goes on the top. If we look at our scale is right here. It's 1 centimeter to 5 centimeters. I'm doing new divided by actual. So that would be 1 divided by 5. And that equals our new, which we don't know, divided by our actual, which is 126 kilometers. If I wanted to calculate this, I need to cross multiply the 126. This gives me 1 times 126 divided by 5 equals my new, which I'm putting as a question mark. If you wanted to write new instead of question mark, that's fine too. You put this part in your calculator. So calculate that. 1 times 126 divided by 5, and you get an answer of 25.2 is my measurement, my new measurement on my map. So for us, it would be 25.2 centimeters. Awesome. Hopefully these calculations are starting to get a little bit more clear on what's going on. We'll do one more with the ladybug, and then you can try some practice. So question 3 says the ladybug is drawn using a scale of 10 to 1. What does the scale mean? The scale means that for every 1, we're going to say centimeters again. It should have said that. For every 1 centimeter, the ladybug is, we draw 10 centimeters. Perfect. That's what it means. Part B. If the ladybug measures 7 centimeters long in the picture, how long is the actual ladybug? Okay, we are looking for actual. That means I want to do my actual length divided by my new length. And I start by building my ratio. So my ratio was 10 to 1, right? That's what it told me up here in the question. I want to put the actual on top and divide it by the new, which is 10. And I'm going to say that that equals the actual length of my bug, which I don't know, divided by the new length of my bug, which was 7 centimeters. Right? It told me 7 centimeters in the picture. Once I've set up my ratio, that's the hardest part. Now all I need to do is cross multiply that 7 to here. That leaves me with 1 times 7 divided by 10 equals question mark, which is my actual ladybug length. If I put that in my calculator, 1 times 7 divided by 10 is 0.7. So the actual length of that ladybug is 0.7 centimeters. Wonderful. I know scaling's hard. I know ratios are hard. Setting up the fractions is hard. So you're going to want to practice for sure. You might even want to rewind and watch a couple of these examples again because it's usually pretty confusing at the start and it gets better the more you do it. I hope that you've been staying safe, have been enjoying your time. Get outside, go for a walk, do something. Just make sure that you are keeping away from other people. I guess that's our lives now. Best of luck. See you soon, hopefully.